Okay. People that I show is not here are Chad, Jaron, and Toussaint. We're going to first review stuff for the exam, and then we'll continue on with the particle in the box with things that are relevant to it, but will not be on the exam. Particle and box, the parts that we completed last week, are still potentially on the exam. So, material for the exam. First, the relativity parts. We talked about a space-time invariant, and we talked about two space-time invariants. One that I actually did the calculation for. The other one is actually in your equation sheet. So the one space-time invariant is that the radius of a circle of light is going to be equal to x squared plus y squared plus z squared, or equal to ct in any reference frame. So our invariant is 0 is equal to the radius squared minus the x squared y squared z squared version of the radius. So it's an invariant that's equal to 0. That invariant that's equal to 0 gives it some unique properties. We didn't talk about these unique properties. The other invariant is E0 is equal to, see, now I have to think about this. E0 is the invariant, and I think it's E squared, E0 squared C squared is equal to E squared C squared minus P squared C to the fourth. That's the other invariant, or you can divide everything by the C squareds and make it like that. E0 is equal to E0 squared, I forgot the square, is equal to E squared minus P squared C squared. That's the other invariant. We didn't use it, but it's just the other invariant that is commonly used. Now, what's important about these invariants? For these invariants, we were able to work out, so I'm not going through all the math, obviously, that we did in class. We were able to work out how we can transform variables x, y, z, and t from one reference frame into another reference frame. So these are the Lorentz transforms here, and these are the inverse Lorentz transforms. What's the difference? Oops, z, not s. The difference is if you're going to the prime frame or if you're going to the unprimed frame. So these are simply equations to transform. Note that for simplicity we use x0, which is the speed of light multiplied by time. That makes it simple because then it has a dimension of distance, the same as x, y, and z. So we have all the same dimensions in our transformations, and we just have these two here. This assumes motion in the x direction. Okay, that doesn't even make sense. V is parallel to x. We define the x direction as the direction of v because then there's no change in the y and z.
And then you'd be expected to derive these or just do these?
No, you'd be expected to use these. So that's the relativistic stuff we did, the Lorentz transforms, and then we did the addition of velocities. Addition of velocities, I just did the definition of velocity, dx dt, velocity in y direction, dy dt, and so on. And then we just used these Lorentz transforms. These are the Lorentz transforms for time and position. I'll wait till you take the picture before I go back to screen. Here I had x0, and here I have time, so I had to divide everything by c to go from x0 to time. You already took a picture of this one. Oh, okay. I don't know why I'm trying to manage her picture taking. And so you should be able to do the work to go from this set of equations here to these two equations here. There is the transformation of velocity from one frame to another in the x direction. That's something that's moving parallel to the velocity of the other frame, or the y direction, something that's moving perpendicular. And remember, our textbook made the funny assumption that there would be like nothing special for the transverse motion. But there is, because of the time dilation. Even though there's no length contraction for transverse motion, there's still time dilation. So that is the end of our relativity portion. Then we had the quantum physics portion. So the only quantum physics that we did was that particle in a box problem. What do we call this equation right here? Schrodinger Equation. Or you may pronounce it differently because I am just not sure how to pronounce it. I'm pretty sure the SCH is not pronounced B, but I could go check again. So we have the Schrodinger equation. Now this is not the one that I showed at the beginning of the lecture last week. What's different between this and what I showed at the beginning of the lecture last week? Yeah, because the one last week was time and position. And then I separated it into a time-dependent and a position-dependent. And so position-dependent called time-independent. So this is the time-independent Schrodinger equation, which we can use in certain cases when the potential energy is not time-dependent, is that certain case, basically. So if our potential energy is just a function of position, that's why I put V parenthesis X. Then we have, this is our time-independent portion, and we have the time-dependent portion that we could solve separately. What's the origin of this equation?
Energy balance?
It's an energy balance, yes. This term right here, this is an operator for kinetic energy. So if I have the operator and the operator acts on the wave function, it gives me the value of that thing. So this thing operating on psi is going to give me the kinetic energy multiplied again by the wave function psi. So you have kinetic energy operator acting on psi of x is equal to the actual kinetic energy multiplied by psi of x. I said operating the first time and multiplied the second time. What's the difference? This is a function that includes a derivative. This is just a number. That represents a number. So they represent different things. That's why I use the term operator versus just multiplied by. So we had this Schrodinger equation, and then, boom, we solved it. What did we do in that solution? You should be able to do that solution.
So just the gap between should and could.
Do what solution? Get from the previous step to here?
Get from that to, this is the solution right here. This is the solution set. So how do we get to this solution set?
So you like break it into zones?
Okay, I broke it into zones. Now that we've gone through the hard part of it, what was the simple logical statement to give me these two portions of the wave function? Very simple logical statement. Look at the picture. Okay, why is the probability of it being outside zero? It would take infinite energy if it's going to be outside of the box. So assuming finite energy for the particle, a pretty solid physical assumption, then it's impossible to have the particle outside, so the wave function has to be identically zero outside of the box. So we did all of the math to show that the math gave us a wave function of zero outside of the box, but I could have simply said, because it can't have an infinite amount of energy, It has to be identically 0 probability of being outside. Yeah.
Why do we have a plus and a minus for example again?
Because we had two solutions. When we did the solution in the middle, right, our Schrodinger equation is minus h bar squared over 2m d second dx squared of psi plus v psi equals e psi. There's our Schrodinger equation. So I rearranged that to solve for the derivative. Do I have to have a partial anymore? No, because I only have one variable now, x. There's no time. Hence, a partial and an exact are exactly the same thing. So it doesn't have to be partial at this point. So rearrange it to solve for the second derivative, and we have that result. And then I gave you, because you don't have differential equations under your belt, that the solution for this is psi equals e to the bx. So you took that psi equals e to the bx, you take our condition. What was our situation inside the box? Only one thing written, hence only one answer you can give. V equals 0. So we took v equals 0, and so this becomes a simplified equals minus 2m e over h bar squared psi. And we said, well, let's take the second derivative and just plug it in. Right? You don't have the math to find that that's the solution, but you have this math to take that solution and put it in. And so when we took that derivative, each derivative just brought down a b, so it's b squared psi. And the only way this can be true is pretty clear. If b squared is equal to minus 2me over h bar squared. I am now to the point of being able to answer your question. If I want to solve for b, what do I have to do? I have to square root it, but when I square root it, I get two results. You always get two results when you square root. And so I had b is equal to plus or minus, and then I just said ik, where k is equal to the square root of 2me over h bar squared. Where's the I come from? Square root of a minus gives me imaginary. I knew that's where you're going. So now that I have this, I have two solutions. I have the psi plus, which is going to use the plus sign, and the psi minus that uses the minus sign. So that's where the two answers came from. This here is the straight solution that I just found, and then I used Euler's formula to expand it to a cosine and a sine.
So will those four equations be on the equation sheet?
This equation will be on the equation sheet, and this equation will be on the equation sheet, and this equation will be on the equation sheet. That's three equations.
And we have to go from there tomorrow.
Okay, then what did we do next? I told you here. Obviously, if it's on the test, you'll have to know. Applied the boundary conditions. The wave function is continuous at both boundaries. Well, since the wave function outside is 0, that means that it must be 0 at both boundaries. Under normal situations, there's a second condition that says the slope must also be continuous. That is, the derivative with respect to position must be continuous. But because of the infinite boundary, we don't have that condition. So this is unique in that form. So next I took and said, I'm going to have psi 1, well, I guess I better find the total psi. The total psi 2 has to be a linear combination of the two solutions. So that means it's some constant 1 times psi 2 plus plus some constant, other constant, times psi 2 minus. So psi is going to be, I'll use A and B. A cosine of kx plus I sine of kx plus B cosine of kx minus I sine of kx. Right, the top one, that was psi 2 plus, the bottom one was psi 2 minus, using Euler's formula. Notice I have cosine added together, so that's equal to A plus B cosine of kx. And then I have the signs are subtracted, so plus I times A minus B sine of kx. Now, A and B can be complex. So I times A minus B can be real, and A plus B can be real. All you have to do is have the imaginary parts of A and B are opposite sign, and the real parts are the same sign. And all the same, the real parts are the same magnitude, the imaginary parts are the same magnitude. That would make all of this real. Psi does not have to be real, but just pointing this out. Now that I have this done, now I'm ready to apply the boundary conditions. So I do psi 1 at x equals 0 equals psi 2 at x equals 0, and psi 2 at x equals a equals psi 3 at x equals a. Right, the value psi 1 was on the left-hand side. It was the one at x equals 0. So that's why I've set psi 1 equals psi 2 at that x value. And then psi 2 is equal to psi 3 at the other side of the box at x equals a. So that's why I have those. Of course, psi 1 and psi 3 were both zeros. So this gave me 0 is equal to a plus b. What's cosine of 0? 1. Plus I a minus b. What's sine of 0?
0.
0. Right away, what can you determine from this equation?
A equals negative B.
Okay, or more simply, a plus b is 0. Yes.
Wait, what is K?
What is k? K is defined.
Yeah. So why did K, wouldn't it be the cosine of K, not the cosine of, I mean, like if,
Well, it's kx, and I'm doing it x equals 0.
oh, right, never mind.
So k times 0 is still 0. Okay. So this tells me that a plus b has to be 0. So a equals minus b, I believe, is what you said. And so this term over here, I could just make it, 2ai instead of ia minus b. Yes, question?
Is this time independent?
Yes, this is time independent.
Position dependent?
It's dependent on position for sure.
And
Okay, then we have our second equation here. The second equation gives me 0 equals, so since a plus b is 0, I'm not going to rewrite that. And I'm just going to have I times 2a sine of k a. Well, if the left side is 0, there are two things that would make the right side 0. What are the two things? A is 0. Capital A is 0. Well, if that's the case, then our psi is 0. And if our psi is 0, then that means we have no particle. That's the trivial solution, and we throw that one away. Don't say, ha ha, I've got it. There is no particle in the box. We're going to find the solution that is a particle in the box. So what's the other solution? Not just 0. Sine of Ka is 0, which occurs when Ka is 0, but it also occurs when Ka is pi or 2 pi or 3 pi, etc. And so this gives us the condition that come on, come to Papa, that Ka is equal to n pi, where n is equal to integers, 1, 2, 3, 4, etc. I didn't say 0, and we started by saying Ka is 0, didn't we? Why did I not say 0?
Another trivial solution, probably.
It's another trivial solution because then it's always 0 for any value of x. Right? Sine of 0x is always 0. So that's why it can't be n equals 0. Now at this point, we can identify the energy because I now know Ka is n pi, but what was K?
That's
Square root of some stuff.
I believe it was 2me over h bar squared. And so if I square everything, I would have k squared a squared equals n squared pi squared. And then substituting for k squared, that would be 2me over h bar squared a squared equals n squared pi squared. And thus energy. Now, because I have the energy n's, I need to put a subscript n on the energy. And so my E sub n is equal to pi squared h bar squared over 2ma squared, all multiplied by n squared. And so I now have quantized energies for my particle in the box because in order for me to have a wave function, the only way I can have a wave function is if I have one of these energies. Yes?
it's probably a stupid question, but would we be given a value for n, or would we just be like, here's the general solution?
I could ask you find for the n equals 3, or I could say find the general solution.
Can you scroll up real quick just to see where this can connect?
I'm not sure what part you wanted to see, so
The part right before we jump down, right there. So, what is? So we're trying to find. So we won't know what A is at the end of this.
capital A.
Yeah.
We didn't work it through last week. That's part of where I'm going to continue the lecture today. Define what capital A is.
But we won't have to find that on the.
Right, you won't have to find that on the test because we didn't cover it last week. That's correct.
Thank you.
Can you guys go back up real quick? A little more. Okay, I just
Too
wanted
far.
to say that what I have written.
Not as funny as it sounds.
Okay.
All right. So we now have found the energies, and we know that our psi sub n is equal to, at this point I have I2a sine of, and yes, I can make it the simplest by putting, what did we have up there? Oh, it was Ka, right? Ka or n pi. Well, I'm going to put n pi over ax. Now, I think that's right, but I'm going to scroll back up just to make sure I have that correct. So I had sine of kx was what I started with, right? Sine of kx right here. So since it's sine of kx, then my k value is n pi over a. So this n pi over a was k. So I could have put kx or n pi over ax. I put n pi over a because a is a simple constant, n is a simple integer, and pi is a simple constant. So that's less complicated than having k, which is a complex, by complex I mean complicated, constant. Having this three simple. All right, so this equation here gives me my wave function. Now I have the I2a. I2a, a was just a constant, right? We didn't know what it was. So I am going to simplify this and just say, let's put a different constant. I'll call it constant c. Actually, on the next slide, I think I'm going to call it constant a, but it's just a random constant. I can just combine in the 2 and the I into the constant. There was nothing special about the 2 and the I other than I started with a constant. I multiplied by stuff to get a new constant. So there's my solution, and that's where we ended up. So yes, here I called it A again for that constant. So psi of n is equal to A sine of n pi over ax. And the energies are there. And so we graphed these out, and we said, where would we be most likely to find it? How do we go? We did have that part, so I'm not done with what could be on the test. How do we find where it would be most likely to find the particle? Okay, remember the probability density was psi mod squared. And so if I square this, for the case of n equals 4, I get something like that. And it's most probable to be at one of these 4 locations. And it has absolutely 0 probability of being at these bottom locations. So if I take a measurement and it's in the n equals 4 state, I might find the first time that it's here. I might find the second time that it's here. How did it go from one position to the other when it's not possible for it to be at 3 positions in between those? Yeah, it's the wave nature. The wave nature says that it's filling the entire box, and when I make a measurement, these are places I'm likely to find it. So if it was filling the entire box, it could be anywhere. It's just I can't find it at this location. It has 0 probability if I measure finding it there. That was a question I asked my teacher when I was in college, and I asked, so, does it just move through that not allowed state? And he was all, yes. Thank you. That really helped. Okay, so that ends what would be covered on the test. Any questions about the test material before I go forward?
Yeah, what is it?
Well, it's either on the relativity stuff I covered or on the quantum stuff I covered.
So Lorenz transformation things.
Okay.
Well, or the velocity of addition, how you went from Lorentz transformations to the velocity of additions.
Including that Lorenz transformation things.
Okay, so now moving on. What's the expectation value? Who knows what the word expectation value even means?
The value you expect.
Okay, the value you expect is a good, straight English translation. And of course, its meaning is from that. So, I forgot I had this in between. I have that question, and then I have this slide before I get to the expectation value slide. Let me do this slide before I forget and skip it completely. How do we find that constant? Remember, I have psi of n is equal to a. I probably should put a subscript n. It's going to turn out that it's the same a for all n's. But in reality, it could be a different constant for each n. Sine of n pi over ax. I have that sign, that function. How do I find the value for a? We find the value for a by using our normalization condition. Normalization is not something you can use plain English translation to know what it means. Normalization means the sum of all probabilities equals 1. Basically, that's saying I'm going to have one particle in my box. If I say, what's the probability of finding it here, and I do that for all positions, it's going to come up to 1. So that means the probability of having the particle in the box is 1. Makes sense. If you have a particle in the box, the probability of having the particle in the box should be 1.
How does that help us find C, though?
Like this. How do we find probability? Probability of x dx. A fundamental important thing that we talked about in general physics class multiple times. Started by talking about electromagnetic waves and light.
Something squared.
Right. It's going to be the psi mod squared dx. So if I'm going to add up all of the probabilities, what do I have to do? Integrate. I have to integrate over all possible positions. Now, in theory, my box goes from 0 to a, but all possible positions would be from minus infinity to plus infinity. So in theory, I have to integrate from minus infinity to 0 psi 1 mod squared dx, plus from 0 to a psi 2 mod squared dx, plus from a to infinity psi 3 mod squared dx. I'll write it down. One is equal to the integral from minus infinity to 0 of psi 1 mod squared dx plus the integral from 0 to a of psi 2 mod squared dx plus the integral from a to infinity, it's an infinity there, of psi 3 mod squared dx. But what is trivial about this calculation? Psi 1 and 3 are 0. So the theory and practice, you have to integrate over all space, but since it has 0 probability of being outside of the box, I really only have to do inside the box for my integration. And so let's do that. I have 1 is equal to the integral from 0 to a of, first I do, by definition, psi mod squared is equal to psi star psi. Psi star is the complex conjugate. So if a, well, I better not use a, if d is equal to g plus ih, then d star is equal to g minus ih, where g and h are just real numbers. That's what the complex conjugate means. I just changed the sign of any I that occurred. No matter where it was. If there's an I, I change its sign. In this equation, once I change it to a, it's just going to be a star sine of n pi x over a. That's psi n star. And then let's do psi a sine of n pi over a x. Then dx. So I have to do that integral. Answer your question. Go ahead and just ask it.
Is that an X or a star inside the first?
That's an X.
Okay.
Sorry, I'll lower it so it doesn't look like it could be a star. How would you do this integral?
It's a goldfish.
You do what? With goldfish?
You change the X now, it looks like a goldfish. Sorry, I got it before, I'm tired. How would you do the integral?
Yes.
That's the nicest X I've ever seen.
Are we what?
I said, are we allowed to call it sine squared n pi ax
You can do that.
with an a star?
Since the a's are constants, I can just put a mod squared outside, integral from 0 to a of sine squared of n pi over a x dx. Now what do we do?
The integral of sine squared.
Look up our integral tables.
Yeah.
I do this integral I do it graphically. All the rest of the integrals we're going to look at today, assuming time should last that long, we're going to do normal calculus way. But I do this one graphically. Because if I do sine squared n pi over ax, x going from 0 to a, that means I'm going from 0 to an integer multiple of pi. And so sine squared does a complete cycle between 0 and 1 every time you go from 0 to pi. So if I graph this, here is sine squared of n pi x over a. Here's x stopping at a. It's going to be doing something like, okay, move a out. Actually, I'm going to move a back. There's a right there. Boom. This happens to be n equals 2. If it was n equals 3, I'd have 3 humps at n the same place. Well, what's the average of a sinusoid squared? The average is where?
Well, from that graph, it's 1/2.
And it always is. So average equals 1/2. So when I do this integral, it's the same as if I just did the integral of 1/2 from 0 to a. Right? Because the integral is adding up everything. And so I just have the height times the width, the area of the box. That's what the integral means. And so the area of this box is just going to be 1/2 for the height times the distance a. A is right there. So this distance here is a. This height is 1/2. And since the average of that function is 1/2, then the area under that curve is 1/2 times a. So that means that I have 1 is equal to a mod squared times a over 2. Solve that for a. A mod squared is equal to 2 over a, square root both sides. And I have the square root of a mod squared, which is just the magnitude of the constant. The magnitude of my constant is square root of 2 over a. It could be multiplied by -1. It could be multiplied by I. It could be multiplied by anything else that has a magnitude of 1. But we just go ahead and say, since it can be multiplied anything with a magnitude of 1, let's just keep that.
I'm confused. Why? So the integral of sine squared times all of that is just a over 2?
Yes. That's a graphical solution to calculus.
But wouldn't it still be... Like, wouldn't you still have n pi over a? Like, wouldn't you have the inner part? Because that seems like that'd be this... It's the same as the sine squared of anything.
Well,
Wouldn't you take
the key here is how many cycles am I going through? And I'm going through always an integer number of complete cycles of a sine wave. And so the average for a sine wave is at the center if you're doing a complete cycle. If you're not doing a complete cycle, it's not.
And then you'd have to
Right,
use
but because of the n pi over a and then going from 0 to a, I'm always going to be doing an integer multiple of cycles. So the average is always going to be 1/2 for my lengths.
Okay, so then the a comes from... That's just the... Okay, never mind.
That's the size of the box.
0 to a, yeah.
Okay, so this we call the normalization calculation. Now, if we look at the top of my slide, I have two things here. The solutions have to be normalized, but they also have to be orthogonal. Orthogonal is a multi-dimensional form of perpendicular. Now, we've learned normal, right? When we used the normal direction, that was a three-dimensional form of perpendicular. Orthogonal is any dimensions. So in 2 dimensions, orthogonal means perpendicular. In any dimensionality, it means they're all perpendicular. So the normal direction to the table was perpendicular to all lines you could draw on the table. So it was orthogonal to all of the lines you could draw on the tabletop. So what does that mean in terms of these functions? These functions represent a direction in space is the way we think about it. So we talk about a Hilbert space that has an infinite number of directions. An infinite number, not just 3 dimensions in space, not 4 dimensions with space and time, an infinite number of dimensions. And each one of these n's gives me one of the dimensions. But they all have to be mutually orthogonal. If I said mutually perpendicular, you take that 2-dimensional word perpendicular and you're broken when you start trying to think about an infinite number of directions. So it's a mathematical word that we only need to use in higher dimensions. So we have this thing that's called the Kronecker Delta. The Kronecker Delta. And what it is if the 2 indices are the same, it's equal to the 1. If they're not the same, it's equal to 0. That's what that Kronecker Delta means. It's a math symbol that has exactly that meaning, 0 and 1.
But why are the little subscripts?
Why are they the same in the first one?
Well, no, like when we go back to the what's typed out, why are they different?
They're different because I have 2 dimensions, the m dimension and the n dimension.
Okay.
And so this is like, if I have sine of 3 pi over ax and sine of 2 pi over ax. So they have to be orthogonal. How do I calculate that orthogonality? The expectation value is my next one, so I have to add another slide in between. I do. I have it written right here. Here is what the function part of psi m star psi n is going to look like. Now remember, I'm going to have the a there, so I'm going to have to take this and multiply it by a mod squared, which was 2 over a. So I have the 2 over a because of that a mod squared. And then this stuff is equal to 2 over a times that stuff. Notice these 2's are going to cancel. And so my integrand here is going to be 1 over a times this stuff in brackets. Don't look around. They all know what they're doing, Chad. None of them are looking confused. So if m is, let's start with the integral we just did. If m is equal to n, what do I have for the argument of this first cosine? It's 0. What's cosine of 0 always equal to? 1. So if m is equal to n, this would be 1, and this would be cosine of 2n pi over a x. Well, if we do the integral of cosine of 2n pi, yeah, that's a pi, a over ax, from 0 to a, we're going to be integrating a cosine over 1 cycle or 2 cycles or 3 cycles. What's the average of cosine? Not cosine squared, cosine. 0. So this one here, when I integrate, it's going to give me 0. Every time. No matter what m and n are, it's always going to give me 0. Question?
Why did the x move to the outside?
It's not on the outside. It's in the inside still. I see what you're saying. Up here. Yes. Better? Except for now I have too many parentheses. We'll just use a parenthesis and a bracket where only one would be necessary. So if m is equal to n, this is 1, so I'm going to be doing the integral of 1 over a from 0 to a. It's kind of not a tough integral. And it gives me 1. If I do the second one, I'm going to be doing the integral of a cosine over an integer number of cycles. It's going to give me 0. But what if m is not equal to n? If m is not equal to n, then this first term here is going to be an integer multiple of pi over a, cosine of pi over a times the integer x. The second one is also an integer multiple of cosine of pi over a times x. And if I go through even an integer number of half cycles, because cosine starts at its peak. You go to a half cycle, and the average for that half cycle is 0. So if I do an integral over an integer number of half cycles starting at x equals 0 for both of these, they both come to 0. I don't even have to do the calculus. I could answer it all by thinking about what the functions look like. I said I was going to do them all numerically because that's what I did before class. But when I was in class, suddenly it made sense to think about the graphs. Isn't it lovely to think about the graphs? Sometimes. You're full of fun. So they are indeed normalized because if m is not equal to n, the integrals of both these terms are going to be 0. If m is equal to n, only the integral of the second term is 0. The integral of the first term ended up giving me 1. It was normalized. That orthonormality is required of your wave function. So you always, when you're finding the wave function, you go through all of the steps we've done here. You solve the Schrodinger equation to find the form of the wave function. Then you set the boundary conditions. The wave function has to be continuous across the boundary, and if it's not an infinite barrier, the slope, the d psi dx, has to be continuous across the boundary. And after solving those, you should have a wave function that only has one unknown, that constant. Actually, I say one unknown. It could be 2 or 3 unknowns. Then you use normalization to figure out what those constants have to be. It's a lot of math, isn't there?
Yes.
And with this, I was able to do a lot of hand-waving graphs instead of doing the hard math. Question?
Can I look around confused now?
You can look around confused now, Chad. Yes.
Does that make sense?
Okay, now let's get to that expectation value. Expectation value. With quantum physics, you have an operator acting on a wave function gives you what we call an eigenvalue, the value that operator, that quantity has. So x operator acting on psi gives me the x value times psi. Now, you're looking at me all strange. You would feel comfortable now, Chad, if you looked around.
Why?
If you are in position space, the x operator is just x. Momentum operator, we saw, was not so fun. That was the momentum operator. So if I want to find the momentum, I have to take this operator and act on the wave function, and it gives me back the momentum times the wave function. Except for who sees a problem? Anybody see a problem with that? Let's do it.
I see a problem.
P operator acting on psi of n of x is equal to h bar over I d dx of square root of 2 over a sine of n pi over a x. What do I get when I do that?
Tears?
No, not tears.
I like that.
I what? What's the derivative of sine?
Cosine.
Ha! But then I have to do times the derivative of the inside, so I'm going to have times n pi over a. Now this should be equal to my momentum value times square root of 2 over a sine of n pi over a x.
What?
Right, that's the definition. P operator psi needs to be p value times psi. So this here is my psi. That's psi of n. Here's my p value. What's the problem?
Where's your p-value?
Well, I have to match up to that equation, but where's the problem in matching these two lines?
We were cosine and sine.
Yeah, one has a sine and one has a cosine. So here we have a problem, and that's part of why we have the uncertainty relation. My solution for position doesn't allow me to know what the momentum is. If this wave function was a function of a momentum operator and a a function of the position operator at the same time, there'd be no uncertainty relation. I would know them both exactly. But that uncertainty relation says it's not possible to know them both exactly. That's why this doesn't work out. I mean, well, that's why. The uncertainty relation is the result of the fact that this doesn't work out. I'm out of time. Poo. Well, to find the expectation value, the mean position, you just take the integral of x times the probabilities. And to make that happen, we put psi star, the operator, psi. And we won't do any more because we're out of time.
This we won't be tested over, right?
That's correct.